All right.
Welcome. Thank you so much for coming. I'm Barbara. This is Ansel, and we're here today to talk about Unicode and strings. For those of you that aren't familiar with our work, Ansel and I are the co-founders of CppCon, which is a GUI framework. We're also the founders of DoxyPress, which is a documenting program. We'll talk a teeny bit about those at the end and let you know how to obtain source code and binaries. And we also have a few other libraries. The point today is to introduce the CS string library. If you are writing a program and you use strings, if you have input that takes strings, if you have output that takes strings, and especially if you're not dealing just in the United States with ASCII and Latin 1, you need to understand strings and why std string doesn't really handle strings.
So as we go through and talk about the Unicode-aware string library we've developed, we want to start by establishing some definitions and some terminology that belongs to Unicode so that we're all on the same page as we go through this. So the first piece of terminology that you need to really understand to understand strings effectively is the idea of a character set, and this is nothing more than a collection of symbols. Importantly, it does not include any values. This is just a list of symbols that someone might use to represent things in strings or any text. So for example, we're all here in this room are familiar with the Latin character set because it's what all the signs in this building are written in. There's other character sets like Greek, used in the Greek language. There are many all over the world.
A character encoding is the values associated with a character set. Unfortunately, the character encoding has a name which actually doesn't make sense. It should be really called a character map, and that's what we're going to refer to it as.
Unfortunately, the Unicode Consortium decided this was called a character encoding, which conflicts with another term we'll define. So refer to this as a character map because it maps symbols to values. When you combine a character set and a character map, you get what's referred to as a coded character set. This is a defined set of symbols and the values associated with them. And one of the most common ones that nearly every programmer will be familiar with is ASCII. It's a coded character set. There are many others that have been used throughout various computing endeavors. Things like ISO 88591, which is very common on the Windows platform, or ones like KOI 8R, which is common in Russia. There are literally thousands of coded character sets in use.
A code point is the term we're going to introduce and is the way you should talk about characters in a string. We're not talking about just the symbol. We're not talking about a particular letter. We're talking about a code point. And the reason we need to talk about a code point is it is the atomic unit. It's 32 bits. Once you start encoding, that may take up more space or less space depending on what encoding you're using. But a code point is the key term that we're going to talk about as we start talking about the library and how to move code point by code point.
It's important to note that code points require 32 bits to represent accurately. At this current point in time, there are only 21 bits of that value used, but there is room for expansion. If you're not allowing for the fact that all 32 bits may be useful, you will have issues down the road in forward compatibility. Another term that's used when you start looking at how to represent strings in some concrete way is a storage unit, also called a code unit in the standard, although we think storage unit is a bit more descriptive. And this is the atomic unit of storage that is used to represent the strings in your program. So in UTF-8, which is one of the more common encodings, a storage unit is 8 bits. And every character is represented by some multiple of these storage units. In UTF-16, a storage unit is 16 bits. Another term which is very important is the basic multilingual plane. And you can look at the basic multilingual plane as sort of the beginning of the Unicode standard. It's the first 64,000 symbols, and these are exactly the set of characters which fit into 2 bytes in the UTF-16 encoding. It contains most characters you would encounter on a regular basis, plus a lot of mathematical symbols.
ASCII is commonly referred to as 8 bits, but it's not. It is a 7-bit character set. And it's only 7 bits, and this is something that people want to believe. It's Latin 1 that goes into 8 bits. But when you're talking about ASCII, and ASCII was really the beginning of setting up a character set. And we're going to find that the first 128 characters in ASCII appears the beginning of Latin 1 and the beginning of Unicode. And this is where most people in the United States and working in English find that that's all that exists, which isn't true. The characters go much further.
So if you ever find yourself saying, well, that's just 8-bit ASCII, stop. That's not true. ASCII is 7-bit. If it involves 8 bits, it's some other character set. For example, it might be Latin 1, otherwise known as ISO 8859-1, very common in many parts of the world. It's an 8-bit coded character set. It includes ASCII as the first half of the code points, but it adds additional ones to support non-English, still Latin scripts. It's a superset of ASCII, so many people use the terms interchangeably. And this is just one of a large number of other coded character sets that support various languages throughout Europe and many other places.
There's actually Latin 2, 3, 4. There are other Latin sets. So you can't just say Latin. Latin 1 is a specific character set. But you will find most of the other character sets in European languages.
So Latin 1 works great if all you want to do is represent a select handful of European languages. And you don't ever need to use the euro sign because it was introduced after Latin 1 was standardized. So there's various places where Latin 1 simply won't suffice. So we need to move into a more general description of symbols and code points.
The reason why we started with the letter A, the Latin capital letter A, is everybody knows this is 41. What can get confusing is what the values are when we start encoding. But as an example, since it's 41, when it's encoded in UTF-8 or it's encoded in UTF-16, we say 41, but it's actually not true. In UTF-8, it's 41. In UTF-16, it's 0041 because of the number of bytes. And this one becomes very, very easy to see. What becomes a little more complicated is if we move to letters that are outside this range and we need more bytes for encoding.
So for example, there is a symbol in the symbol area of Unicode called the rightwards arrow with corner downwards. It looks like this, and you'll note that every Unicode symbol is uniquely identified by 3 things that go in concert. The shape of the symbol, or it might be a non-printing symbol in some cases. Its name, this is in the Unicode standard, specifically named rightwards arrow with corner downwards. That is a defined name. And its code point or code position. That's the U+21B4. And that is a value that is not in any encoding. That is the raw value that is specified in the Unicode table for this code point.
When you're encoding in UTF-8, as you can see, it's going to take 3 bytes. So again, this is where it becomes really obvious in a value like this, because 21B4, that is just an assigned value by the Unicode consortium. Once it's encoded in UTF-8, we're at 3 bytes, and UTF-16, it is 2 bytes. What's really important to notice, this is 1 code point, not 2, not 3. So every single code point has how much storage it takes. And these are variable number of storage because they are different amounts. But it's really important to remember this is 1 code point.
So if you correctly interpret the first string here as UTF-8 and the second string as UTF-16, they are equivalent. They contain exactly the same data. One code point, its value is 21B4. They are just represented differently in memory. Now, as I mentioned, if we step outside the basic multilingual plane, we get to some more obscure characters. So in this case, we have an eighth note, musical symbol eighth note. And you can tell it's outside the BMP because its Unicode value of U plus 1D160 has 5 digits in it. So therefore, it exceeds 16 bits. It's outside the first 64K, thus it's outside the BMP. In order to represent this symbol in UTF-8, we use 4 storage units with these values, and there is a representation in UTF-16 as well. It uses 2 16-bit storage units, and each one of these storage units is what's referred to as a surrogate. This is a feature that was added to the standard when code points grew from 16 bits to 21. It would be ambiguous in UTF-16 if these values were ever legal code points. So essentially, in the Unicode table, this range from D800 to DFFF were reserved. They will never be assigned to any valid code point. So when a UTF-16 decoder sees a value in this range, it knows that this is a surrogate. It needs to be combined with the following surrogate to form a complete code point.
The same thing happens that these are not valid in UTF-8. One of the differences between UTF-8 and UTF-16 is in 16, we have the surrogate pairs. In UTF-8, they are multi-byte. So to know that there is a surrogate, you would go to the Unicode table in UTF-16, and there's that range. In UTF-8, as by looking at the high bits, you can see that we need more bytes to generate an actual code point. That actually makes UTF-8 easier to decode and encode and understand than UTF-16.
And an unfortunate accident of the existence of UTF-16 is that since it's unable to represent certain values in the space of code points, we must reserve those for use by all implementations. So they're not available in UTF-8, even though they could be represented in UTF-8, because they would not be representable in UTF-16, and they must be harmonized.
Unicode code points are 32 bits. This isn't negotiable. It is part of Unicode. So it does become the question of why are we using UTF-8 and UTF-16? Why aren't we using UTF-32? And we're going to talk about that and why 32 becomes wasteful and 8 is becoming the optimized way for encoding.
So I've alluded to UTF-8 in several points previously. UTF-8 is a variable length encoding. It's capable of representing every code point in the Unicode standard in a sequence of 8-bit storage units. And it has a lot of very nice properties. For one thing, if you're working with ASCII text, then the encoding is the identity encoding. So ASCII text is unchanged when you encode it as UTF-8. Also, whenever you have a multi-byte character in UTF-8, its values always have the high bit set, so they can never be confused for any ASCII value. So UTF-8 encoded text, for the most part, will pass unchanged through legacy programs that expect 8-bit encodings. Another very important property is the fact that since we're dealing with individual bytes here, we don't have to worry about the platform endianness of strings. It's very helpful. In order to do UTF-8 encoding, you need to be able to determine how many bytes it's going to take to encode a particular code point in memory. And this process is simpler than it is in UTF-16 for some cases.
We do have some code we're going to show you when we go over the library that's going to show the difference of how you do an encoding for UTF-8 versus UTF-16. And the math and the code itself is just easier and less error prone in UTF-8. UTF-16 is also a variable length encoding. This is some of the differences. If you've looked at the Unicode standard and you've seen that some languages use UCS, and there are encodings we're going to talk about very briefly that preceded UTF-8 and UTF-16. So you have to ask, is an encoding a fixed length or is it variable? And UTF-8 and UTF-16 are variable, as we've shown that it can be 1, 2, or 3 bytes, or you could go up to 4 in UTF-8. There was a time that UTF-8 went up to 5 and 6, but that was disallowed in 2003 by the Unicode Consortium.
The real downside to UTF-16 is that it gives you a false sense of security. The problem with UTF-16 is that it's both too wide for things like ASCII and Latin, so you waste up to 50% of your storage space for strings that don't need multi-byte characters. And it's too narrow to contain the entire Unicode set, so you have to deal with all the complexities of a variable length encoding anyway.
Some of this started early on when people were trying to choose what encoding they wanted to use. And Microsoft kind of set the standard way back when. And they did choose UCS2. UCS2 being a fixed width and a predecessor to UTF-16. Other languages followed suit, and it really seemed like a good idea. Everybody was like, well, this is the way to go. We use UTF-16, and in some ways, now, looking back, it's like, we didn't really think this through. And in fact, the Unicode Consortium felt the same way, that we didn't think it through, and now what? Now we're partway through, everyone is using UTF-16, what do we do?
And at a certain point, they discovered that all of the symbols used in all of the world's writing systems throughout all of space and time are not going to fit in 16 bits. So they had to grow the code point size, and this removed a lot of the advantages to a 16-bit encoding. So most languages and operating systems that have come more recently to support Unicode have used UTF-8, both for backwards compatibility reasons and also for the quality of implementation it allows.
Joel on Software is a blog that if you're not familiar with his work, you should Google him and take a look at his work. This is a quote that he put down in 2003. It's really valuable because if you don't know the encoding, you can't interpret the text. He ran into this a lot with email. And email was set up to be encoded, and some were using one encoding, some another. There's a gentleman who actually did a commentary on this particular blog. And he looked at some text, and he said, well, I'm going to just guess, because I'm sure I can guess the encoding. And at one point, he decided it looks like a DNA sequence. And that's where he went with it. And then he kept trying different encodings, and nothing actually fully encoded it. And then somebody told him it was kanji. And when you look at the numbers, and then you look at kanji, they're not similar at all. So it really turned out you cannot guess. So again, if you're writing any software or dealing with strings in any way, you need to decide on an encoding, and you need to either inform your users or have it set up some way in your software or the library that you're using that it understands the encoding.
So the most fundamental takeaway from this talk is that if you have what you think of as a string and you don't know what encoding it is, you don't actually have a string. You have a sequence of integers which are without meaning. It is of the utmost importance to know what encoding every single string in your program is, or you cannot understand what it means. So let's look back at the history of how we got into this state. The original version of Unicode came out in 1991, and the major encoding that was used was UCS2. It was 16 bits, per storage unit fixed width encoding, because again, they thought that was all the characters we would ever need.
Something happened in 1992, and actually reading the history of this is quite fascinating. Ken Thompson and Rob Pike designed UTF-8 on a napkin. They were contacted by a particular group,
X-Open was asking for a better standard to encode characters.
And it's a very interesting story. Rob has actually published, and he used to work on a project where he had them pull up the old server so he could prove the emails of a gazillion years ago that this is actually the way it happened. And they developed this, and they got UTF-8 working in Plan 9, which those of you Linux people are familiar with Plan 9, that didn't quite go where they wanted, but it did do UTF-8 in about 3 days.
Unfortunately, it took a long time for people to realize that UTF-8 was going to be a good idea. So in 1992, as they were developing UTF-8, other companies started adopting UCS2. It seemed like the way to go. In 93 was when the Unicode consortium realized they'd hit the 64K wall. They were going to have problems. They had to expand the code point. So they released a new encoding system called UCS4. This is a 4-byte fixed width encoding. And everybody said, my God, 4 bytes for every single character? There's no way we can do that. That's wasting way too much memory. So nobody used it. UTF-8 was widely publicized that year. It was introduced in Usenix.
But it wasn't until 1996 that it was adopted. And this is actually amazing to me to realize it was 1996 that UTF-8, and they did come out with UTF-16 the same year. But then companies still didn't make the change. And we're talking about Microsoft and Java and a lot of other companies. They didn't make the change, and it was available because they didn't understand the power, which unfortunately means changing over later becomes more difficult. The other key thing to notice here is that Google has done some studies on the availability of UTF-8, and they've released some statistics. In 2012, it's been estimated that 50% of the internet now uses UTF-8. As of September of this year, it's 90%. And that's email, XML, HTML. So the internet is going UTF-8.
So if you have any connection to any sort of network server in your code, you need to be able to handle at least UTF-8. And the great thing about UTF-8 is almost every network server supports it at this point. So it's the only non-ASCII encoding you need to support. You don't need to worry about any of the legacy character sets. You just deal with UTF-8 and you're done.
And this year we have actually released CS String. And the reason why we did it, we're going to show you an example in a few minutes here of how mangled data can actually get if you're not following your own rules of using UTF-8. And we have released CS String. It is a BSD licensed library, and it is standalone. You can use it in your C++ applications. We've also incorporated it in our CopperSpice GUI framework. Under QString 8, we are developing that class. So if you are a CopperSpice user, you'll be able to use UTF-8 directly in the GUI environment.
So let's step back for a second and talk about how some of the other libraries that are out there handle strings to sort of form the rationale for why we decided that yet another string library would be of value. A large part of what we've done in the CopperSpice project is look at places to improve the existing code that we were working from. And we discovered challenges along the way in many different parts. And once we got to a certain point, we realized that the string handling was really subpar. So we decided to look at it in more detail. And we realized that in our other projects, we were also running into trouble with Unicode string handling. We thought, there's a theme here. This isn't just unique to a large framework library. Everyone needs to work with strings. Everyone needs a functional way to work with strings that actually works. And we said, okay, well, what is out there? Well, the first place to look is the standard. So we have std string. Does that give us any help? No, none whatsoever. There's std string, which might as well have been called std vector char for all the help it gives you for strings. I mean, yes, there's some string operations like substring, but it really doesn't understand text. It has no way of representing encoding at all. It just deals with a sequence of 8-bit bytes. There's stdw string, which might be 16 bits, or it might be 32 bits, depending upon your platform. There's some interesting behavior there that's implementation defined, and it really doesn't help you that much because it still doesn't give you a way to specify the encoding. We need Unicode strings, not std string. So we looked at other libraries. Well, as I said, std string has no encoding. What does Microsoft do with MFC? Well, they started on UCS2 and they moved to supporting UTF-16, mostly.
QString in Qt is, well, it started out as UCS2. They have migrated to UTF-16. There's a few issues, though, with QString, and that has to do when there are surrogates. And the problem is, if you're using Qt and it's in this encoding, Qt itself doesn't always deal with the surrogates, and you have to glue them back together in your code.
And this is a very common behavior in libraries that started with UCS2 and then were extended to support UTF-16. They leave a lot up to the programmer, and it's easy to get things wrong. And a great example of this, I'll take a moment to pick on C# here. Every one of these libraries has similar issues, but it's one of the most demonstrative ones. In C#, there is a text field element in the GUI library, and you can specify the length that you want a user to be able to type in characters. But it's not really characters, it's storage units. So if you, for example, take a text field and say, I'd like the user to be able to type in 10 characters. And they type in 9 characters that are in the basic multilingual plane. Those each take 1 storage unit to encode. And then at the end of the string, they type in a character outside the BMP. It will insert the high surrogate, fail to insert the low surrogate because there's no room for it, try to report the error to the user, and in the process of displaying the string, attempt to render an invalid UTF-16 string to the display, and it crashes the .NET runtime. This is an example of just how badly things can go wrong when you have a library that claims to support UTF-16 but doesn't take care of all the corner cases. And since nearly every character that's used in common usage is inside the BMP, these bugs can lurk for years until someone hits exactly the right corner case and discovers it and crashes your program or breaks your security system or what have you. This is incredibly dangerous. So there must be a better way.
So as we were working on DoxyPress, which is a documenter, and our main focus of enhancing DoxyPress, which is a fork of Doxygen, if you're familiar with that, we wanted to be able to parse C++. And we actually use Clang as a front end for parsing, not a Lex parser or anything like that, so we can truly leverage what's already out there. Parsing isn't something we need to reinvent. We need to take the output and feed it back in. Ironically, we found problems. The original versions dealing with DoxyPress use things like QC string. And these were way back in the late, like 1999, like a long time ago. And these weren't actually handling strings the way we think of them.
They were basically giving you the same amount of support for strings as std string does, which is to say, none. They just treat it as a bag of characters. So we went through and refactored all of this code to use the QString class from CopperSpice, which is UTF-16. And we figured that this would make a great improvement in the ability of DoxyPress to handle non-ASCII characters.
So what we have here is a problem we found. The QString text here This text is just text in English that's going to be displayed on a particular page, some HTML output. And this is the code it was being run through. We'll come back and take a look at this code in a second, but basically M1 is calling M2, and then it's printing out. But then we decided, hey, we're international. We should actually test in some other languages, not just English.
So we translated the string into some other languages.
And I think that's pretty good German. If we have any Russian speakers, we've been told this may not be exactly what the English would say, but it's close enough that that's kind of the interpretation. I can at least tell that looks like Russian and looks like German. Ansel speaks a little bit of German, so when I was testing this, and this is real world case, I asked him to come over and look at it and say, is this really German?
Well, I looked at it, and what I was actually looking at was this.
That's not exactly German, and just so that you know, we did not put carriage returns into this Russian. This is exactly what came out in DoxyPress. As we were running it through, we got this out, which is sort of telling us we had a UTF-8, UTF-16 problem because we're not using UTF-8. We were using QString.
And here we are working with a UTF-16 compliant string library, and we got garbage out the other end. What happened?
We have been told by some friends from Ukraine that is not Russian. No way. So what was going on? Let's take a look at the code.
The problem here is that we have a string. As I mentioned, QString is in UTF-16. We're calling a legacy piece of code that wants a const character star. So we take this string and we convert it to UTF-8 because that's a great encoding to use. You can represent every Unicode character in an 8-bit string. So any function that takes a const character star can receive this. So we call M1, it's fine. M1 is passed data, which points to a UTF-8 encoded string. Then M1 calls M2. There's an implicit constructor for QString. It receives this data. It assumes the data is in Latin 1. It's not.
And there's no way to tell it.
So
not in QString. And again, this also happens in many other languages. We're just using this as an example to show you that code like this just doesn't work unless you know the encoding.
So when we interpret this string as Latin 1, we get garbage out the other side. This is an example of how insidious it is to have a string in your program that does not contain encoding information along with it. As I said, every string must be tagged with its encoding or you can't interpret it correctly. If you have if you have any code in your program anywhere which does not know what encoding the data is it's working with, you will have problems of this form. So we need something that always guarantees it knows what encoding it is.
CS string to the rescue.
So
what are we going to retain as we're building this library? And what do we need to change? We did start by looking at QString and STD string.
And we realized that 8-bit storage is a good thing, for one thing. It covers the vast majority of text use cases in a more efficient way than 16-bit. Also importantly, as I mentioned, it guarantees that if you have issues with multi-byte encoding, you'll find them quickly, because nearly every non-English character will exercise those code paths. But what needs to change? Well, we need to support encoding. We need every string in the program to be tagged with its encoding. And we really want to deal with Unicode because at this point in computer science, all of the other encodings are basically historical artifacts. And we wanted an ability for people to add new encoding formats as different things become available without having to change the implementation of the string class.
So our idea was to write a library where the iterators, the class, the basic string was all set. And that we have one class where the encoding exists. And that's all you need to modify and change and enhance to add a new encoding. But we needed to define what comprised the basic, and we're calling that CS basic string. It does allow defining your own allocators. We actually don't spend much time going over that. If you need to set up your own allocator, the library will take an allocator that you can pass to it.
What's important about using CS basic string is the fact that regardless of the encoding that the string is stored in, the user always sees a CS basic string as a sequence of 32-bit code points. You don't need to deal with the complexity of UTF-8 multi-byte sequences or UTF-16 surrogate pairs or any other variable length encoding in any representation that you might be using. And it supports conversion between these existing encodings as well.
So this is what it would look like. We have just set up some usings so that you can type it easier. This is part of the library. Currently, the library does support UTF-8 and UTF-16, and we're going to show you how easy it is to add another encoding. But first we had to say, wait a minute, what is a string? And these were some of the ideas we came up with of what a string is, which is why this topic became so interesting to us, and it actually becomes very complicated because all of these do satisfy the definition of what a string is. But how do you handle each one of them?
And it's really important to understand the distinction between a few of these that we'll start looking at here. So, what data types do you see in these examples? Because many novice C or C++ programmers will look at that and go, oh, I see a bunch of strings. But as we all know, data types are quite distinct and can be complex. Would anybody care to guess what data types exist on the first line of code in here?
So ABC, the quoted string ABC, is a reference to an array size 4 of const characters.
Yes.
And zero 1 is a pointer to const car.
Very well said.
Yes.
And
I have implemented string classes.
Yes, that's very good.
very well said.
ABC is also referred to as a string literal, but most people aren't really sure, and they just read it as a const character star.
Mm-hmm. So let's break these down piece by piece. So for our purposes, we're going to call a const character star a C-style string. Many people have used that definition. It's a little easier to hear. It's initialized with a string literal. A string literal, being an expression, has to have a data type because the string literal is the expression itself. Its data type is array of 4 characters. As he noted, there's also a const in there and a reference, but the important meat of the definition is that it's an array of characters, char type. On the second line, when we assign str1 to a CS string, this is unsafe because we don't know what encoding it's in. We have no way of knowing. This is a const character star C-style string variable that came in from who knows where. This is not safe. On the other hand, in example 2, we have a CS string that's being initialized with a string literal. These are not the same. And the reason it's important that these are not the same is because we want to be able to tell the difference between these two cases. Because if you're initializing a string with a string literal, we know what encoding your string is in. We can safely convert it to a CS string. This yields a lot of API benefits. If we don't know what encoding your string is in, this is unsafe, and we need to make this explicit or give you other ways to disallow it in your code. And it turns out that it's actually fairly easy to tell the difference between these two cases in a string library. So we have separate constructors in CS basic string. One of them which takes a string literal, which if you work through the data type manipulation, needs to be a constructor that takes a reference to an array of any size of const character. And then we have another one which allows passing in pointers, but this can be either deprecated or disabled depending upon your needs in your application. Well, why do we do this? because we had an API requirement for CS string, string literals are really important for API quality. If you can't use string literals in your code when you're manipulating strings, it becomes very difficult to read because you have constructor calls or conversions littering anything that works with strings.
Okay. So this was, yes, we're here. Okay, so we're on sample code.
Yes, we are.
Sample code.
Okay.
And another type of string literal.
So there are many types of string literal that were added in C++ 11.
11, yes. Go on. It's okay. The U. This is not as well known, but you can specify a string literal, so you can specify the encoding. It was added in C++ 11. The syntax may not be gorgeous, but at least it works. Please note that UTF-13 or 32 is not supported. We're not quite sure why, but they did not, or they supported that one. The unsupported, we have not. Which one am I on?
UTF.
Unsupported. Yes, currently supported. Ones that are not supported. The annoying one is const care.
Yeah.
Why wasn't that const care 8T, Richard?
This is a terrible.
This
is a terrible feature in the standard, because it means that as a library implementer, you can't tell the difference between a string literal, which is in the compiler's runtime encoding, and a UTF-8 string literal, which is in UTF-8. This is really unfortunate. So we can easily support string literals of the UTF-16 and UTF-32 type, but it's ambiguous on the UTF-8 type.
We actually have a define in the library that you can turn on and off depending on how restrictive you want to make it.
So if you do happen to try to pass a string literal containing a multi-byte character without specifying a Unicode encoding, you will get a warning from your compiler. And this is because the behavior is implementation defined here. And the behavior on the compiler that we use most often, GCC, is in most cases to encode this string literal in UTF-8, which then, when the string is parsed in a different encoding, creates some issues. So this is something to avoid. You should make sure that you have this warning turned on. If you suppress warnings, you probably don't want to suppress this one.
So the design of the library, CS basic string, it really encompasses everything we need to do. It's pretty much a drop-in replacement for std string. We have written all the methods, find, there's a lot of find methods. We have added numerous ones. And everything in CS basic string, again, it calls the encoding. So nothing needs to change in the basic string class. It does everything you would want it to do. We have also started to add find fast. And we are adding that in various places to do things that return an iterator, not an index. And this has become very powerful for us in CppSpice when we want actually to deal with iterators and not indexes. If you start breaking down the code and really looking at what it takes to do all the methods in std string, you'll find that everything is index-based. But again, it is really nice to have iterators. It's easier to work with. It's actually easier to, you're not dealing with off by one errors as much, which we're notorious at finding.
So inside a CS basic string, we have a vector that contains the raw data. In this case, we'll be looking at UTF-8, so it contains a UTF-8 encoded string. So we have a private data member called mstring that is this vector. And the beginning and the end of this are vector iterators. Well, we don't want to expose the vector because we don't want to expose the raw underlying stream of bytes. These are private, so we want to give you a way to access the data without having to deal with the complexities of encoding. So how do we do this?
We want to actually be able to walk code point by code point. So what we did is we drew a graph here, because like we said, internally, we're dealing with the std vector. But outside, as a user, we're dealing with the CS string. The reason why this slide becomes very powerful is you can see the rightwards, downwards arrow is 3 bytes. So if you're looking at it in a vector and you were walking, the string length would look like it had 3 bytes for that, but it's 1 code point. And when you're walking the string externally or in an application, you want to be able to walk code point by code point. So here's the encoding. This is all it takes for us to add UTF-8, 16, you want some other encoding. This is all you would have to write. This is the class for UTF-8. We'll show a little bit of the implementation, but it's a using and a couple methods. That's it. That's all it takes. You define these, there's a new encoding in the library.
So we distilled the functionality that a string needs in order to work with an encoding down to this very simple API. So it's very easy to implement new encodings. And so here's an example of what the insert method looks like in UTF-8. And if anybody here has actually worked with a UTF-8 encoding, this code will probably look fairly similar. It's just a bunch of straightforward boilerplate of doing some bit shifts and manipulating things into the right arrangement for storage in the UTF-8 format.
This was actually very easy to test because we either put in the right characters and got it out, or we didn't.
And the second half simply deals with the 3-byte and 4-byte UTF-8 encodings. Again, nothing terribly complex or high-tech here.
Once you test the off by 1 errors and they're fixed, the encoding just works. So when we ran through some of the testing, Ansel wrote some not so human readable, not so pretty testing and did about 1,200 tests. I wrote a little bit more human readable stuff that tests about 85 different outputs. One of the great things is he tested everything that he could test against std string. So that gave us a lot of confidence in the work we were doing.
Mm-hmm. And as an example of some of the testing, we can do things like this, where we can manipulate multi-byte characters easily without having to deal with the complexities of how they're encoded in the string. So we can just append a character outside the basic multilingual plane, and it just works.
The tests here that we're showing, these unit tests here, they are part of the source code. So if you go to our forum or our GitHub, these are actually included, so you can take a look at them.
Here's another example of a test which ought to be really easy. Every string library on the planet ought to be able to do this innately. Try this in your favorite language that claims to support Unicode strings and see how much work it is to actually get the right output. Just walk through a string in reverse and print each symbol. It is surprising how much code this takes if you have a library that does not give you the support for putting back together code points from the representation. And then again, just simply erasing the first character from the string and repeatedly printing it. Give this a try in your favorite library. You will be surprised at how badly it will come out. And if you're in C#, you will probably crash the runtime.
Here's another test that we did. And the only thing we're trying to point out is the storage versus the code points. Because when we show that graph, we show that if you were walking the vector, there would be a larger size. So we did include that method in the library if you wanted to see how long it would be in terms of the size of the internal representation in the vector. And by the way, we are looking at changing the vector to be a small vector for optimization.
So we're in the process currently of taking the CS string library and integrating it back into CppCon. And we're going to gain several benefits by doing this. First and foremost, that it will gain support for UTF-8 strings, which are much more efficient and better designed.
We have about 75% of the QString methods working in QString 8. It was very interesting, like implementing things like to be able to normalize in upper and lower case. When we were reading some of the existing code of various libraries of what it takes, using our library, our CS string library, the code size went way down. We didn't have to ask, is this a high surrogate? Is this multi-byte? Because we were just walking code points. So our code got much smaller and much easier to read and easier to test. We even got to resolve an issue that was actually broken in DoxyPress. And this is because you can do parsing with using the Lex parser and not using Clang. And the Lex parser turned out to be broken, which was quite interesting as we were trying to display some documentation during our own testing. And we couldn't figure out why UTF-8 and UTF-16 were broken. And then we realized the parsing was broken.
So earlier when I said UTF-8 is designed to pass unchanged and undamaged through most legacy code, the key word there is most. Not all legacy code deals well with characters outside the 00 through 7F of ASCII, and this turned out to be one such case. So examine your parsers carefully for what they do when they encounter non-ASCII characters. Make sure it does something sane.
And we did correct this in the Lex parser, but if you're going to use DoxyPress, use Clang for the parsing. So this is sort of why we did everything. We're working on CopperSpice, we're working on DoxyPress, and we needed ways to handle strings. So this is kind of just an overview of how everything comes together for us as we are integrating everything back into QString 8. And as we do this in CopperSpice, we're going to be able to add some using statements and then do a QString at a UTF-16 and have everything there based on our library. We're also going to be able to remove some of the wrapper classes and some of the complexity internally. We have already done some studies, and we're expecting to see the internals of DoxyPress in many places shrink by 50% because so much of our internal strings are ASCII and Latin 1. So basically, just to let you know, like I said, we released this library earlier this year. Ansel's released a libguarded library that is going to be presented tomorrow. And we also have a signal slot library for delivery of signal slots that are based on methods and not classes. So we have these 3 separate BSD libraries, and we have CopperSpice, and we have DoxyPress. We also are thinking of some other things we want to do, but we're trying to keep the number of projects we're doing down to just this because we think we have enough. We're on GitHub. We have a website that has a form that you can download any of our source. Everything is open source. Everything we can BSD, we do. We also started a YouTube channel about 2 months ago, and we crossed over to 400 subscribers, and hopefully we'll be much higher by the end of this conference. Our YouTube videos are on YouTube/CopperSpice. Our aim on these videos is to show CopperSpice, DoxyPress, and C++. We just did 3 videos that go through data types and value semantics. And in these videos, we take it from the beginning of what is a data type all the way through value semantics and pointers and references. And on these videos, we really explain why you can't call a reference just a reference. So all of these things are available. We're here all week to talk about all the products that we have, and we would love to have contributors on the work that we're doing. We do have a couple people that have been doing some extensive testing on the string library, and one of the gentlemen who is here at the conference, he says the more he is using our library, the more he realizes STD string is broken and insufficient for the work he's doing. So, are there any questions? Yes.
All right, so I'm a Rust.
Oh, we actually have a microphone.
Oh, we actually have a microphone. Excellent.
Oh, thank you.
I don't have to repeat the question.
So I'm a Rust programmer.
Yes.
And we obviously have a UTF-8 string library in the standard library. I don't know why that's obvious, but we do.
Okay.
It's pretty good. And one of the things that was worrying me when I was watching your presentation was you have this kind of thing where you have indices. And what worries me about that is when you have graphemes that are multiple code points. So people kind of start, it's the same issue you have with UTF-16, right? Is people start to think, one code point is one displayable character. But if you're doing that like reverse iterator example, unless you actually like pay attention to like NFKC and everything, you're going to have an issue where you'll print an E and then you'll print the thing that goes on top of the E.
The accent, yes.
Yeah, the accent.
Yes.
So to respond to that question about graphemes and grapheme clusters and stuff like that, that's version 2, for one thing. The design basis for CS string was, let's design a container that is capable of representing Unicode strings without mangling them. Adding the ability to process grapheme by grapheme is, in my vision, a layer above that, because the code point is the atomic unit of text. And so that will probably be a translation layer that is built up atop CS string.
Right.
That can give you a grapheme-based iterator.
The thing that Rust does is it has like iterators for code points, and it has iterators for bytes as well, but it doesn't let you index into a string, which is something that I think is a good thing because it forces people to think and forces people, like in my compiler, I have to use a Unicode library in order to deal with that kind of stuff.
So with respect to not having the ability to index into a Unicode string, I can see that when you're starting from a clean sheet of paper, that makes a lot of sense. And our goal was also to be sort of a gateway drug to be a less harmful version of STD string.
Okay.
And people expect some sort of index-based semantics. You may not get exactly 100% correctness if you have very complex combining characters, but at least you won't generate invalid Unicode to the level that a library that allows you to put just a bare high surrogate in a string will do.
What we've also been doing with CopperSpice is we've written normalization, composition, decomposition. So we're kind of spending some of our effort, what does it take to upper and lowercase? What does it take to compare?
Yeah.
So we've done a lot of this in CopperSpice, not with the idea of just leaving it there, but the idea of once we figure out exactly the best ways, how to do that. Like you're saying, I have a layer 2 of the library.
Yeah.
We didn't want to do it wrong.
Yeah.
And so it's really like, right now you would have to decompose the string. But we've learned a lot about strings just writing this decompose in QString 8. So we can understand what does it take. And when you start getting into the accents and the graphemes and just a language, because we do mostly tandem programming, and when we couldn't communicate, it became complicated.
Yeah.
So we're nowhere near done with what we're doing, but part of this is to find other people who want to contribute, add more encodings, and to find out what's missing.
Yeah, cool.
But right now, as a drop-in replacement, we think we've covered most of that.
We've improved on the current situation in C++. But thank you very much for your feedback.
Wonderful
this
feedback.
helps us know that we're actually going in a good direction, I think. Any other questions?
Okay. Well, we appreciate it. If you think of questions, we're here all week and we're online, and thank you so much for coming.